Hey, how you doing? This is Mel Strong, and this lecture is an introduction to humidity. Now, before we get into humidity, we're going to talk about the composition of Earth's atmosphere. So, this visual here represents the gases that make up Earth's atmosphere. And it doesn't matter where you are, the composition of the Earth's atmosphere is pretty much the same no matter where you go. So, the atmosphere is about 78% nitrogen and about 21% oxygen and about 1% argon. And right there, you're about 99.9% of all the gases in the atmosphere. There's a little bit of CO2 and a little tiny amount of everything else. So before we go on, let's talk a little bit about these gases because it's worth knowing a few things about them. So with nitrogen, what this visual is saying is that right now you've got more nitrogen going in and out of your lungs than any other gas. So my question is, what is it doing for you? And the answer is absolutely nothing, because nitrogen is what we call an inert gas. What that means is that it really doesn't react with anything. And in order to get nitrogen to react with something, you've got to have really, really high temperatures before any kind of reactions occur. So as it goes in and out of your lungs, your body just ignores it. Now it turns out your body needs nitrogen, but it can't get it this way. And that'll come up later in future lectures. So oxygen, is that an inert gas? Oh no, this is very reactive, right? And this is why we need it, because it, what we call, oxidizes. And so we need that for our respiration process. The oxygen accepts electrons and gets converted in our body from oxygen to carbon dioxide. Argon is another inert gas and also very heavy. So in other words, it's a very dense gas. Maybe this is one you haven't heard of before, but if you have seen thermal windows, like double pane windows that are built to insulate, in between the gas they usually put argon. And the reason for that is because the gas molecules are so heavy, they're really slow, and they bump into each other very slowly, and that's how heat is transferred. So argon gas makes pretty good insulation. Then we've got carbon dioxide, and we're going to talk all about carbon dioxide much later in the semester, but this is a greenhouse gas. So those gases right there make up, like I said, 99.9% of all of the gases in the atmosphere. So here's another way to look at that. We could break this down, and again, you can see that there's nitrogen at 78%, oxygen about 21%, argon at 0.9%. Add those three together, you got 99.9%. In fact, that's 99.95% or so. And then all these little traces of gases, and some of these you've heard of, maybe some you haven't, all add up together. So there's a little bit of other things in the atmosphere. However, of all the gases that are shown here, there's one gas that you are breathing right now, that's in the atmosphere right now, and it's not on this list. And that gas is water. Water is never shown in a graph like this, or in a list of atmospheric gases. And the reason is, water vapor is considered a variable gas. So that means that it could range from close to zero all the way up to maybe 4% in certain parts of the world. If you're in New Mexico, it usually ranges from about 0 to maybe close to 1% of all the gases in the atmosphere. So the reason it's not shown in the graphs that we've been looking at, or the tables you might find, is because all those numbers have to add up to 100. And so if I go back to the previous graph I was just looking at here, so all these numbers add up to exactly 100. So if I had 2% water, those numbers wouldn't add up to 100. I have to adjust them all. Or if I had 1% water, then they wouldn't add up to 100 again, and I have to adjust them all. So what they do in all textbooks and all references with atmospheric gases is they call this the dry composition. So dry gas composition of the atmosphere. This is what all the gases of the atmosphere would look like if there were no water. But there is water. So you got to take that into account. So that's why they never list water on these tables because it's always different from day to day and depends on where you live. So humidity is a way that we describe how much water vapor is in the atmosphere. And there's several ways to do it. And in this lecture, we're going to learn 2 different ways to describe humidity. In the next lecture, we're going to learn a third. Now, the way that would probably make the most sense to you right now is to talk about the percentage of gases in the atmosphere that's water. So we just talked about this, how you could have 0 to 4% of the gases in the atmosphere be water vapor. Turns out, though, that's actually not the way we usually do it. The first method that we're really going to get into is something called mixing ratio. And mixing ratio describes how many grams of water vapor there are in every kilogram of air. And it's often written as a fraction. So here we have mixing ratio equals grams of water vapor as the numerator and kilograms of air as the denominator. Now the conventional way to do this is to think about a single kilogram of air. So I box up some air enough that I have 1 kilogram, and I want to know in that box how many grams of water vapor do I have. So that's kind of the way we're going to think about this. So you might see mixing ratio written something like this. Mixing ratio is 3 grams per kilogram or 3 grams per kilogram. And the assumption here is that you know that grams means grams of water vapor and kilogram means kilograms of air. Okay. Now, the thing is, before we get any further, I want to make sure that we can visualize what this means. What does it actually, what does a gram of water vapor look like? And what does a kilogram of air actually look like? Okay, so we're going to talk a little bit first about the metric system. So in the metric system, when they were inventing it, they said if you have a cube and the cube is exactly 1 centimeter on each side, 1 centimeter on each side. Okay, 1 centimeter by 1 centimeter by 1 centimeter. The volume of that is 1 cubic centimeter. Okay, and it turns out if I fill this cube with water, that I will have a mass of exactly 1 gram. So 1 gram of water would look like a cube, could fill up a cube that's 1 centimeter on each side. So what is a physical object that you can think of that's about this big? So there's a couple of them. I can think of one would be like a sugar cube. What I usually show everybody are dice. So a standard die is about 1 centimeter on each side. So 1 gram of water would look like, imagine if these were little ice cubes, right? Each one of these would be about 1 gram of water. So when we talk about, say, back to this, 3 grams, the mixing ratio is 3 grams per kilogram. That 3 grams means 3 grams of water vapor. Think about, okay, I'm going to take water vapor that's in the air, I'm going to condense it down to a blob, and that blob, in this case, I would have 3 of these guys. I could fill up 3 of these little cubes with water. That's what 3 grams of water looks like. All right? So, before we move on to the kilogram of air, let's just talk a little bit more about the metric system, because also, when they came up with this system, 1 cubic centimeter has another name. It's called the milliliter, or ml. And if you have 1,000 milliliters, that equals 1 liter. Okay, so that's going to come up here in a little bit. Okay, so back to our initial problem. I wanted you to be able to visualize, what does this mean? This 3 grams per kilogram, what does that mean? And the top, so we've said the top is 3 little ice cubes, each the size of a die. The bottom, I want you to visualize a box. And the box has 1 kilogram of air in it. And the question is, how big would that box be? Because we don't think about air as having much mass. Like we don't even think about the weight of the air above us, but it has some. And so it turns out at our altitude, so here in Albuquerque we're about a mile above sea level, it turns out that if you had a box that's about a meter by a meter by a meter, that would be about 1 kilogram of air. Okay, so you fill this up 1 meter by 1 meter by 1 meter, that's 1 cubic meter. So how big is a meter? Think about a doorknob. You reach out to grab a doorknob, and the doorknob is about 1 meter above the ground. Okay, so that's a meter. So imagine a box that big on each side. That's a kilogram of air. Okay, so now imagine this box is now made of plexiglass, and so it's plastic. You can see through it, and there's a little door in it. Okay, and we have filled our box with perfectly dry air, but I'm going to open up the little door, and I'm going to throw in 3 little ice cubes. Okay, so I got 3 grams of water, I got 1 kilogram of air. I'm going to open up the door, I'm going to throw my 3 grams of ice in there and close the door. And so my little ice cubes fall to the bottom of the box, and let's say the box is perfectly sealed, and then they melt. So I got 3 little puddles, right? I got 3 little puddles sitting here at the bottom of water, and then they evaporate. So I come back later, and these 3 little puddles have completely evaporated. So the air that's in there has a mixing ratio of 3 grams per kilogram. We just made it, right? We took a kilogram of air, we took 3 grams of water, we stuck it in there, we let it melt and evaporate, and it's floating around in there. And water molecules, by the way, the oxygen is pretty big compared to the hydrogens, and the hydrogens stick on one side of it, so they look like these Mickey Mouse heads. So you have to kind of imagine you've got this box now with these Mickey Mouse heads floating around in there, these little water molecules, right? We'll see more of this in a little bit. Okay, so imagine I open up the little door now, and let's say I've got a little cup, like a little coffee cup, and I reach in there and I scoop out and I pull out some of that air. What's the mixing ratio of the air inside my cup? It turns out ratios stay the same. They're independent of size. Okay, so if I take a little bit of that air, the mixing ratio of the little bit of air that I got out of that box is still 3 grams per kilogram. Okay, so you've got to separate out the ratios from the absolute amounts of water. So with mixing ratio, there's a number of problems that we can do with this. And I'm going to work out a couple of examples here. So here's one. It says mixing ratio is 4 grams per kilogram. How much water do we have total in 5 kilograms of air? Okay, so if I show this problem to people, generally half the people I show this to think that they should multiply these two numbers, and the other half think they should divide these two numbers. And neither one can usually give me a very good reason why. So with problems like this, I want you to visualize, go back to thinking about a kilogram of air as a box of air, right? So I've got 1 kilogram of air is a box that we said was a meter on each side, right? Okay, so if I have 1 box and the mixing ratio is 4 grams per kilogram, I have 4 grams inside that box, right? Now if I have 5 kilograms, I essentially have 5 boxes. So think about, okay, so that's 1 box, but then I got another one, right? And then I got another one, and so on and so forth. Each one of these has 4 grams in it. So if I've got 5 of them total, then I can multiply, it should make sense to you, I can multiply 4 times 5 for the total amount of water. So I'll write this out with just the units here. So I would take my mixing ratio, 4 grams per kilogram, multiply that by the number of kilograms I have. In this case I have 5. And I'll put that over 1. And if I write it out this way, that unit kilogram cancels that unit kilogram. 4 times 5 is 20, and grams are the units that I have left. So by writing it out this way, I can see which, what I hope is that the units that I don't want to cancel, leaving me the units that I do want. That's an indication that I probably did it right. So we'll do another one. So on this one, it says the mixing ratio is 12 grams per kilogram. So that might be a value that we would have here in the summer during our monsoon season. How much water is in this room? Okay, so let's just imagine we're in a room, and here's the dimensions of the room. 5 meters by 3 meters by 12 meters. So what I need to know to answer this is how many kilograms of air do I have? And I know that at our altitude here at Albuquerque, 1 kilogram of air is about 1 cubic meter. So in order to answer this, I need to know how many cubic meters I have. Therefore, that will tell me how many kilograms I have. Okay? So this is a volume problem. And volume is length times width times height. So I'm going to take 5 meters times 3 meters times 12 meters. And if I do that calculation, 5 times 3 times 12, I get 180 cubic meters. Okay? So that tells me, because 1 cubic meter of air is 1 kilogram, that I have 180 kilograms of air in that room. So now it's just like the last problem. I have 180 boxes of air. Each box has 12 grams of water vapor in it. So to get the total water, I take my mixing ratio and multiply it by the number of kilograms of air that I have. So again, it's like 180 boxes of air. Each box has 12 grams in it. Write it out this way. You should see the units you don't want go away, and the units you do want are left. So I end up with 12 times 80. 12 times 180. And that gives me 2,160 grams. Okay. So I want you to be able to visualize what this means. Okay, so this is the total amount of water. So if we condensed all the water out of the room, right? All the water molecules in this room, we condense it out, we would have 2,160 grams. Well, just a minute ago, I told you that, so a gram of water equals 1 milliliter, or 1 cubic centimeter, right? So that's the same thing as saying 2,160 milliliters of water. That's the same thing. And can you visualize what that is? Well, 1,000 milliliters are in a liter. So 2,000 milliliters is 2 liters. So if I divide this by 1,000, I get 2.16 liters. So think of a 2-liter bottle, right? We have filled up a 2-liter bottle, and we've got a little bit left over. That's how much water we would have if we were to condense all the water out of this room on this particular day. So let's go back to this idea of a big plastic box that we put little ice cubes in. And at the time, what I said was we had a little door on it. We could put these little ice cubes in there. They would melt, then they would evaporate, and we'd have air with some certain kind of mixing ratio. Let's imagine we go back to this box, and I open the door, and I put in 3 more ice cubes. And I close it, and they melt, and they evaporate. And then I go back and open the door, and I put 3 more ice cubes, and they melt, and they evaporate. And I could keep going back, and I could keep putting ice cubes into the door, but there comes a point where if I put too many in there, they'll fall to the bottom, they'll melt, but they will no longer evaporate. Because air has a limit as to how much water vapor can exist in it at any given time. And so we have a term for this. It's called saturation. So what that means, if we talk about the air has reached saturation, or maybe we might say the air is saturated, what that means is that the air can no longer hold any more water vapor. So This is critical because what this means is that there's a limit. There's a limit as to how much water can be in the air at any given time. Now on Learn, or again if you're coming here from somewhere else, on my website, there is a graph that I want you now to look at. So go ahead and download that. And we're going to look at this graph together. It's a table of numbers with a curve. It looks like this. So this table on the left, so the very left-hand column says air temperature in Fahrenheit. And this column here says maximum possible mixing ratio at this temperature. So what it's showing is that if let's say it's 70 degrees, and we've got our plastic box idea, right? At 70 degrees, in 1 kilogram of air, the absolute most water vapor that you could evaporate into 1 kilogram of air is 19.12 grams. So this is 19.12 grams per kilogram. So in one box of air, 1 kilogram box, this is the limit as to how much water that air could hold. And you'll notice that as I increase the temperature, the numbers get higher. Lower temperatures, numbers get lower. And in fact, this graph is what you would get if you were to graph these numbers. It would look like this. We got temperature on the x-axis. We've got maximum mixing ratio on the y-axis. So what this is telling us, this is actually one of the most fundamental laws in weather. This idea that temperature controls how much water could be in the air at any given time. What this is saying is that if you increase the temperature, the air could have more and more water vapor in it. It doesn't mean it has to have that. This is a maximum possible mixing ratio. So let's say it's 80 degrees, right? So 80 degrees, the maximum I could have is 27 grams per kilogram. Could I have less than that? Yes. How much less? Could I have 0? Sure, I could have 0, but I can't have more. That's what this means. Notice as you go down into colder and colder temperatures, the numbers get smaller and smaller, or we get down into this graph. Let's say it's 0 degrees Fahrenheit. Here's 0, right? So at 0, the maximum I could have is about a little over 1 gram per kilogram. So even if the air is saturated, even if it's completely maxed out, the most I could have is a little bit more than 1 gram per kilogram. So this is critical because what this means is that cold air is always dry air. Even if it's saturated, even if it's completely maxed out, it's still dry. Like look down here. Temperatures of minus 20, minus 40, right, are on this table. You've got really tiny mixing ratios that are possible. So one of the rules in weather, in climate, as we're going to get into, is cold air, always dry air. Always. No, there's no way around that. However, hot air could be humid. It could have high mixing ratios, but it doesn't have to, right? So it could be very low or it could be very high. But cold air absolutely has to be dry air no matter what. All right? So we can see the effects that temperature has on humidity if we look at the Earth as a whole. So I've gone to this site, earth.nullschool.net, and this is a visualization tool that shows us the current weather all over Earth. And I'm going to click the word Earth, and I'm going to pick an overlay. It says TPW. That's for total precipitable water. And what this is going to show us is it's going to show us how much water is in the atmosphere. And there's no numbers here, but to the left on the scale, the brown, that's very, very dry air. And then as you get more humidity, more water vapor, it turns more blue, then light blue, and then kind of this white color. I'm going to click the word Earth to make that disappear. And so I can rotate the Earth around and look at where most of the water vapor is on the planet. And what I see is that there's this big band of really high humidity air that's typically found around the equator. So, as you probably know, it's usually pretty hot at the equator, and it's sitting over this open body of warm water. And because of that, the mixing ratios there are usually very high. On the other hand, if I turn this around, say we can look at Antarctica. And Antarctica is very dry because it is very cold, right? And so both of the poles of the Earth are pretty cold, but Antarctica is even more cold because not only is that the South Pole, but the South Pole is about a mile above sea level, so it's much colder than the North Pole. And we see it's very brown, very dry air here. But we can also see some other effects. Like if I go to, let's go over here to South America, and you'll see that there's this brown blob right here. So we'll zoom in a little bit there. So this is all the Amazon basin here. So think about tropical rainforest, right? So pretty humid here. But what's this? Why is this so dry right here? So that's a very tall mountain chain called the Andes. And so high elevation is usually colder temperatures. Colder temperatures mean drier air. So we've got a blob of really dry air here next to pretty humid air. And we can see this in several other places in the world. And again, if you do this yourself, you'll see slightly different patterns than I'm seeing depending on what time of year you're looking. It's winter in the northern hemisphere right now. So we see a lot of dry air over the continents. Cold air that's come down from near the North Pole. Let's look at something closer to home here. Yeah, we're all still pretty dry here. So, overall, if you just kind of look at the Earth as a whole, you will see that we've got a band of pretty humid air around the equator and pretty dry on the North and South Poles. Okay, we're going to do a little thought experiment here. So let's go back to this idea of having a box of air. I got 1 kilogram of air, and there's water molecules floating around inside the air in this box. And I happen to know that the mixing ratio is 9.24 grams per kilogram. Okay, I also happen to know that the temperature of the air in this box is 70 degrees. So one question I could ask, could I add more water molecules to the air inside the box? So if I go to this table and I look at 70 degrees, it says the maximum possible mixing ratio at 70 degrees is 19.12. I'm only at 9.24. So I could definitely add more water to the air inside this box. Okay, but we're going to do something different actually. We're going to cool it down. So let's imagine that I start to cool this box down. So it's at 70 and I start to cool it down to 65, to 60, to 55. And notice what happens on our list of numbers here. As I go down from 70 to 65 to 60 to 55, the maximum possible mixing ratio is also going down, right? So if I get down to 50, well, 50, the maximum possible mixing ratio is 9.24 grams per kilogram, which is exactly what I have. So if I cool this down from 70 to 50, when I get to 50, at that point, the air is saturated. It can't hold any more water vapor. Okay, now, let's say I cool it further. So I'm going to cool it all the way down to 45, let's say. Well, the maximum possible mixing ratio at 45 is 7.64 grams per kilogram, but I'm at 9.24. So as I cool it down to 45, I've got to lose about 2.5 or so grams of water. So as soon as I get down to 50 and the air becomes saturated, as I cool it further, water molecules have to come out of the vapor state, out of the air, and they will collect on the bottom or the sides of this box. So Mother Nature requires that all my little water molecules, the extras, have to come out. and they will start to collect in these clusters on the inside of the box. And the transition from the vapor state to these clusters of liquid, we call that condensation. Right? Okay, so condensation occurs at 50 degrees. And as we cool it further and further and further, we will continue to pull water out of the air as required by the numbers that are in this table. So, let me show this to you a slightly different way. And imagine, here I've got just an image of water molecules here floating around. We don't know how many there are. And it's 80 degrees outside, right? So I start to cool it. Say sun goes down, this is air that's outside, sun goes down, starts to cool, and it cools, and it cools, and it cools, and if it cools enough, eventually we're going to reach the saturation point. And when we do, when we reach that saturation point and then we continue to cool it further, we would start making condensation. So right here we've got the 65 degrees. We're making condensation. This is not rain. This is water that's coming out as drops on the surface. And at that point, the air is saturated. And what we have just made is something called dew, right? So these droplets, and I have to show pictures of this to people that live in New Mexico because our air is so dry that this only happens a few times a year. But when it does happen, the dew droplets typically form on the grass. And the reason is because the grass is very thin, and thin things cool off first. So these are dew droplets that form when the air was cooled down to the point that saturation occurs and cooled even further below that. So if we go back to this idea, this temperature at which this happened in our box, this has a name. This is called the dew point temperature. Or sometimes because we're lazy, we just call it the dew point. So you've actually done this experiment yourself. You've taken at some point probably leftover food, you put it in the Tupperware, you put the Tupperware in the refrigerator, and you come back the next day and you pull it out, and when you take the lid off, you'll notice there's a bunch of little drops on the inside of the lid that weren't there when you put the food in the refrigerator. So what happened there is when you put it into the refrigerator, the air that was in that container had a higher mixing ratio than it was allowed by the temperature of the refrigerator. So you actually made dew in that box in the refrigerator. Now if we go back to this case, this example here, because we noticed the condensation occurred at 65 degrees, on this particular night we could conclude from that the dew point temperature was 65. That's when we saw condensation first start to form. Now let's say I do this another night and I've got less water vapor to start with, right? So there's less water molecules in the air than there was in this first example. It's 80 degrees again. And I cool it down, and I cool it down, and I cool it down. Now last time we hit the dew point here, but we've got less water now. So that means I can cool it further before I actually reach saturation. So in this case, I cool it all the way down to 50 degrees until I finally see that the water molecules start to condensate out as dew. So from here, what we could conclude is that the dew point is 50 degrees because that's when condensation occurs. So, mixing ratio is one way that humidity is reported. The other way is dew point. So in a weather report, they'll often give the dew point as a way to represent the humidity. And the way that works, low dew point means there's less water vapor in the air, which means the air is pretty dry. High dew point means there's more water vapor in the air, which means the air is generally more humid. So the other way to think about dew point is that it describes the temperature at which the atmosphere becomes saturated. So if I tell you, let's say tonight we check the weather and the weather report says the dew point is 45 degrees. One of the bits of information that tells us is that if we cool it down to 45 tonight, we will get dew, right? We'll get saturation. So here's an example of how we might use dew point. So this is a map, and this map has temperatures of dew point in degrees Fahrenheit. And you can see that over here in the southeast, they've got dew points that are in the 60s and 70s. Over here in our neck of the woods, we have dew points that are in the 20s. So that tells you there's a lot more water vapor in the air over here than there is where we live. Another way to think about this, so if you lived, say, in Florida, if it got down to the 60s at night, you would get dew, right? Because the dew point here is like 65, and here it's 70. If you lived over here, you'd have to have temperatures down below 25 if you're in the red zone, or below 20 if you're in the yellow zone. By the way, what happens when you get dew points below freezing? If the dew point is below 32 degrees Fahrenheit or 0 degrees centigrade, then that means that in order to get dew, you've got to get it below freezing. But you're not going to get liquid. What you'll get is frost. And frost looks the same, it's little sparkles on the grass at night. That's when the dew point is below freezing and you manage to cool it below freezing. But it's the same idea. And in the winter, this is a lot more common. You may have scraped ice off your windshield. That's what's happening. You've reached saturation, but the saturation point was below freezing, and your windshield is thin and it cools off first. Another way that we actually use dew point a lot in New Mexico is to monitor the monsoon, and we'll talk about the monsoon in later lectures. But this is something called the dew point tracker. And so if you look at this, on the x-axis, these are dates. There's June 1st, and then there's July 1st, and ignore everything except the blue line for now. The blue line is the dew point as recorded at the airport here in Albuquerque. So when the blue numbers are higher, you have more water vapor in the air. You have higher dew points. Then you'll see them drop. That's low dew points. Dew points are over here on the y-axis. So here we got dew points of like maybe 5 degrees Fahrenheit. They don't have units, but these are units of Fahrenheit. So we had really dry air right through here. Then it got more humid. Then it got a little bit drier. Then it got more humid again, and goes back and forth, back and forth. But notice that once we get into July, we have pretty high dew points for almost the entire summer. Now this graph stops at August 22nd, which is when they made this one. Look for a minute at the red curve. The red curve is what you get if you were to average out all of the monsoons that have happened in the past 30 years. And if you do so, on average, in Albuquerque, what happens is the dew point starts to rise in the spring, and once it rises past this green line is 47 degrees. It rises past this green line for 3 consecutive days. We declare that the monsoon has officially started. And then, on average, again, looking at the red one, on average, the red line stays above this green line, and it starts to dip back below the green line in the middle of September, and then we go into the fall. So dew point is one of the things that we use to monitor the monsoon activity. When we have high dew points, that's usually coincides with what we call monsoon bursts. There's a lot of humidity in the air, a lot of water in the air, and so that's more conducive to precipitation formation. So you see these spikes here, those are times when we probably had more thunderstorms and more chances of precipitation. Or sometimes we go into what are called monsoon breaks, and that's what this is. So this dip here is a period where we were in a very dry, relatively dry air for the monsoon period. And during that time, we probably saw very few, if any, cumulonimbus, very few thunderstorms during that time. So dew point is pretty important here in New Mexico, especially during the monsoon season. So dew point is reported at pretty much all weather stations report dew point. It changes throughout the year. So in New Mexico, it's typically higher in the summer and lower in the winter. And one of the other things that can change dew point, especially where we live, is the wind direction. So we happen to live between, New Mexico's here, and we've got a pretty warm body of water down here, and we have a pretty cold body of water over here, right? So let's say we've got wind coming from the northwest. Where did that wind come from? Well, it came from somewhere to the north where it was probably cold, and cold air is always dry air. Dry air, low dew point. So if we have winds coming out of the west or the north or the northwest, usually that coincides with times of low dew point. On the other hand, if the wind comes out of the east or the southeast, that's coming from a location that was pretty warm, big warm body of water that's usually conducive to high amounts of water vapor in the air. So usually for us, if we have wind that comes out of the east or the southeast, we usually get higher dew points because we have more water in the air.